Hello, hello. Hello, hello, Samuel. Hello, Sophia. Hello, David. Oh, thank God I don't want to be the first. Thank you, David. Good afternoon, David. Oh, more people are here. But hello, Samuel and Sophia and Jasmine and David. And wait, and someone else just came in. Oh, someone else just came in. And good afternoon. Oh, Sophia, you said it for, I'm sorry, I didn't see. Thank you, Sophia. And thank you, David. Good afternoon. Good afternoon. And good afternoon, Samuel. And good afternoon, Jasmine. And good afternoon, Jalen. And good afternoon, Jada. Oh, good afternoon, Jalen. Thank you. Okay. See. Oh, and goodbye, my board. Oh, why? Hold on. Oh, okay. Hold on. Okay, well, I'm getting the board. We're gonna like get right to it today because today. Good afternoon, all smile. Oh, wait. Okay, as soon as we get to it, we're gonna get to it. We're gonna go straight back to where we were in the calculus because schedule's so funny. I want to get. So yes, good afternoon, Samuel. Good afternoon, Jasmine. Good afternoon, Jada. Good afternoon, Olsmael, and David and Sophia. All right, Oh, wait. Okay, okay. Let's get going. Let's get going. And good afternoon, Nicholas. Thank you. Awesome. Okay. Uh, sure thing. Sure thing. No problem. Okay. But I'm just gonna get rolling because I think I'd like to start catching up with myself a little bit with the material. Oh, there it goes again. I can't catch it. Why? Okay. We're just gonna get straight. All right. I'm gonna just start talking physics. Please forgive. Oh, and hello, Nicholas. All right. Awesome. And hello, Sam. Adrejo. Awesome. Okay. I'm going to go straight to physics. I'm starting to fall a little bit behind myself. It'll all work out in the end, but I know I've been hearing about what you've been doing. Good morning. I know what you've been doing in the lab, and it's really impressive. I've been hearing from some of you directly and I know you're ahead in lab of where you are with me. It's always the case, and that's always fine to a point, but I'm sure it's starting to get a little confusing or frustrating to some of you. So I want to catch up to that material that you've already done in the lab. In other words, I really want to get to question 9 of this homework 1. And you also may have noticed, those of you who have handed in homework 2, some of you have gotten it back, some version or another of it. Homework 2 is like, it's sort of like all this huge expansion of question 9 on homework 1, but we haven't gotten to question 9 yet. So it's either repetitious or it's hard. Anyway, my goal is to get to, but I'm aware of all that, is what I'm trying to say. I want to get to question 9 on the homework, but I first have to finish this last bit that I'm saying, because we really need it for later. This last bit that I'm saying about question 4 and question 5, this bit about energy conservation and how it relates to the work integral and all of that. So I'm just going to, all right. So to remind you, so these equations on the board right here, the first equation, I'm now going to assume that the first equation makes some sense to a lot of you, or at least that you know at this point you're responsible for it. I think we established it last time. I believe. Yeah, I'm looking at the other board right now. Yes, like the first equation on the board right now is saying, in short, work is the transfer of kinetic energy, right? I mean, okay, I'll say it's a double equal sign. It is not a triple equal sign. The left side is the integral that means work is being done. I'm pushing or pulling something through a measurable finite region of space. Oh, there goes my board. All right, I'll say this and I'll bring the board back in. So the left side says work is being done on a system. It's being pushed or pulled through a finite, measurable region, interval, displacement of space, path of space. The right side, the sort of new bit from last time, says yes. And you know what happens when you push or pull something through space? What happens is we bring a property of that thing from an old value to a new value. The property we from here on in call kinetic energy. Kinetic energy is 1/2 of the mass of a system times the square of its speed. A very odd, strange combination of constants, of measurables that we wouldn't have thought to care about and put together before. But algebraically analyzing the work interval leads us to realize, oh, when you do work on something, it turns out that you change 1/2 its mass times its square of its speed, like you change the value of that entire product. Generally speaking, you do so by changing its speed. Generally speaking, you don't change its mass, you change its speed, but it could be one or the other or both. But the overall product of the square of its speed times 1/2 of its mass is what you change when you do work on something, and the units work out perfectly as they should, as they would need to, i.e. the units of 1/2 mass square speed are the same as the units of force through displacement. They are newtons times meters, which we call joules. So when you do work on something, when you do positive work on something, you raise, so that 1/2 mass square speed combination, we from here on in give a name because it's that important to track. It's that predictable and that measurable to track. From now on, 1/2 the mass times the square speed of a system, we call its kinetic energy. And we say that when we do positive work on a system, we raise its kinetic energy by precisely the number of joules of work that we did. So I'm saying in the end, I'll put the board back. The board is driving me. No, let's be honest. It's not the board that's driving me crazy. I was already crazy. Okay, but here's the board back. And I still believe, by the way, I still agree with, I think it was Samuel C. who said it's because I don't like touch it enough while I'm talking. I mean, that's probably still true, but I don't know why it happens. Anyway, notice the first equation. It's the second equation that I want to build today. The second equation looks very similar to the first one, but it's the second one I need to explain. But the first equation on the board, notice it does not say that work is kinetic energy. Big misunderstanding that people have. It's not. Work is not equal to, the amount of work you do on something is not equal to the kinetic energy it has. The amount of work you do on something is equal to the amount of kinetic energy that thing gains from your positive work. And where does the energy come from that it gained? It comes from you, the one doing the work. That's why I say work is transfer of energy. If I do 3 joules of work on you, then you gain 3 joules of kinetic energy and I lose 3 joules of kinetic energy. They get transferred from me to you. So kinetic energy is the commodity. Work is the transaction. Like one's more like a noun, the other's more like a verb or something. In the end of the day, if I do negative work on you, that means I pull energy from you and bring it to me. What is energy? It's the ability to do this very thing called work. Energy is something we pass around from one transaction to the next. My energy is my ability to alter some aspect of you by doing work on you. My energy, my kinetic energy, is the ability I have to move you by pushing you. And I have that ability if I am already moving and big. Okay, so that's what the top equation is trying to say, that the amount of work I do to get you from spot number 1 to spot number 2 is the amount of energy you will gain from energy amount number 1 to energy amount number 2. If the left side of the integral, if the left side of that equation, if the integral is positive, then the right side had better be positive. You will gain energy if I do positive work on you and vice versa. Okay. So now I want to show what I mean by the second equation, similar but different, but there's something in the chat. Oh, no problem. Oh, wow, he even went public. Hello, Stephen, no problem. Thank you for your acknowledgement of our humanity, and thank you for being here. Okay, so that was just a quick recap or review of equation number 1, which, oh, by the way, which would be sufficient. Equation number 1 would be sufficient for solving questions 4 and 5 on homework 1, which, yes, I am still talking about as promised. Equation number 1 could be sufficient to solve. You could set up questions 4 and 5 on homework 1 and just use equation 1. You could think about the whole thing in terms of just work and the transfer of kinetic energy. And in fact, we can do, in principle, all of physics that way. But we realize that some forces, when they do work, have a property that we call conservative. And that leads us to a whole kind of certainly quicker and more efficient understanding of the world, maybe a deeper understanding of the world. This is what I mean. Hold on, let me just change the view. Sorry. Oh, and hello, Brianna. Great to see you. Not calling you out, but great to see you and great to pronounce your name correctly for a change. Just okay. Oh, wait. Oh, sorry. That's true what I just wrote, but let me write one other thing. Actually, sorry. All this is true too, but there's a faster way I can say this. Sorry. See, calling Tuesday and Monday just warps my fragile little mind. God, it really is. All right, that's my last mistake I'm allowed to make for the next 2 minutes. Somebody get a timer. That was a mistake, and it wasn't 2 minutes. Somebody get a punishment. Okay. This is what I meant to, I'm looking at, no problem. Thank you. Look at the, you know what I love? Yeah, okay, I'm totally opening up a portal for this. No problem, but thank you for acknowledging, thank you for being here. And it's like awesome that both a person whose name I won't call out, but rhymes with Shmeven, Shmermeho, and Brooke, they both went public with their apology, which really takes even more guts. Anyway, whatever. So now I'm like making it harder for them to be them. Okay. Rhymes with Eve. Okay. All right. Anyway, thank you both for being here, and thank you both for going public with your apology, and thank everybody for, okay. And everybody else is like, wait, he's thanking them and I'm on time? What? All right. So look, here's what I'm trying to say. I wanted to find conservative force for you in a mathematical way. You've heard of conservative forces before. I wanted to find conservative force in a mathematical, calculus-social way here. But in order to do that, and one of the reasons I want to do this, I want to introduce a new piece of notation, a new concept to you first. So you know how we're talking about integrals now. And we're saying in general that work is not only an integral of force, but in fact, specifically, it's this thing called a path integral of force, right? We're saying that work is the integral of force we're saying that work is the integral of the force vector dotted with the displacement vector, where that work is this continuous sum of a bunch of little works that you perform along a path, right? A path integral, technically, a path integral of some function is the integral of the dot product of that function with infinitesimal bits of displacement. The path integral is how much a certain function accomplishes along a one-dimensional displacement, i.e., along a path. Okay, so work is the path integral of force. Put one last final way, it's a path integral as long as, number one, it's a dot product in there, and number two, if the dx or the d whatever happens to literally be dx as in displacement along the x-axis or some similar one-dimensional axis, then that's technically a path integral, okay, as opposed to an integral with respect to time or something like that. Okay, so that's what so work is a path integral. So now I'm saying here's a new piece of notation. There's a kind of definite integral that is called, in math, it's called a closed path integral. And I know someone's here, 1 second. Whenever you see from now on an integral with a circle on it, rather than like a from A to B or from x1 to x2, whatever, if you see a single integral with a circle on it, that means it is a definite integral. It is a definite integral. It will be evaluated. It will ultimately return you a numerical value that applies to some specific region, particularly, for example, a specific region of space. But if you see a circle on it, what that means is we're going to evaluate the integral from here to there, and then back from there to here. A closed path integral is really the sum of the integral from one spot to another, plus the integral going back to the original spot. In other words, a closed path integral is a definite integral, but it is necessarily a round trip. Okay, that's what it means from that. It's a math thing. Whenever you integrate back to wherever you started, we call that a closed integral. And it's a very useful idea in math. And whenever you do it around a path, it's called a closed path integral. So why I'm introducing it is I'm now saying, and I can go back if you want me to. Right. Okay. So from here on in, a conservative force is one that for which necessarily, by definition, we know in advance will do no work, no net work throughout or over any round trip, any closed path. Okay, that's for some forces, this is necessarily true. And for some forces, this is necessarily not true. It's like a big distinction among forces. Tell me if you want me to go back a page, but. Oh, and there's a hand up. Hold on. Give me 1 second. I don't even know who it is. Sorry. Well, let me just. Oh, is it to go back?
No. I have a quick question. So, what was on the previous board before? It says the integral from A to B and then the integral from B to A. Wouldn't those just be inverse of each other?
Okay, that's a really good question. I mean, that's like a great question. I mean, that is a great question. It depends. So I would think that too. I would have thought that also, but it totally depends on how the remember that f of x, we're assuming the function, whatever function we're talking about, is a function of x. So it depends what kind of function of x it is, whether that's the case or not. I'm totally going to show you an example. Like literally the next thing I was going to do is show you two examples, one where this works out like that and one where it doesn't, so you can see. But that's a great question because mathematically it's certainly, oh, I just lost my board. Okay. Mathematically, it would certainly seem like that. But if you remember that f of x is a function of x, like to see, I'll give you the quick answer to answer your question, but then I'm going to show everybody with example. Like if f of x is a constant function of x, like if f of x doesn't change no matter what x is doing, then you're definitely right. Like then in one way, the integral is whatever it is. And then in the other way, the integral is just the negative of that. But let's say f of x is some function like negative x cubed or something like that, then that would mean that when x changes sign, the negative, like that means that the ultimate answer of the function would depend on the sign of the x. So if you were going in one direction, the whole function would go in one direction. And if you go in the other, it would go the other. So the negatives would, I'm going to show you in 1 second what I mean, but I'm just saying, actually, that seems right mathematically, but it won't necessarily be right depending on what the force function actually is. All right, let me get an example will make it more concrete, but that's a great question. So I'll show you right now. Hold on. But do you sort of see what do you sort of vaguely, I mean, I'm sure you're waiting for an example, but do you vaguely see what I'm saying so far, Ismail, or?
Kind of.
Okay, so let me show you. I'll show you with examples, but it's a great question and totally about what I was about to do. So let me just make a list here before I forget. Oh, and you need my board. Hold on. Everybody, give me a second to put the board back. I know you need the board. 1 second. I'm just writing it first. Okay, let me see if I can get the board back. Okay. 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 So first of all, we're gonna now I'm gonna totally both invite and obligate Olsmail when I'm done with what I'm about to do. It'll take like 3 minutes. I'm certainly going to want to know from her and anybody else whether I've really answered her question or not. First, I want to answer it in English, and then I'll try to make it directly mathematically responsive. But Olsmail is right. Like okay. So what I'm saying to everybody is, a conservative force is one for which, if you integrate it out and then you integrate it back, the out cancels out the in, and you end up with 0. The non-conservative force is one for which that is not the case. Now, and Olsmail's quite rightly asking, wait, shouldn't it always work out to be the case? Like, shouldn't all forces be conservative? Okay, I'm going to tell you. So first of all, just in English as a list, I'm going to argue that friction, tension, the normal force, most forces that you might view as contact type forces, they don't turn out to be conservative. And whereas forces like gravitation or gravity, mg or gmm over r squared, the spring force, which we're totally dealing with now, and which is why this is all coming up, i.e. the elastic force, the Hooke's law force, kx, is conservative. And the electrostatic force, which is where we're ultimately heading with all of this in this course, is also conservative. And that's really why I have to make a big stink about this, so we can understand it in the context of electricity. I still want to answer Olsmail's question, but you'll notice one thing about these conservative forces. Okay, notice. So I want to do this in English and then land on the math. But just notice the forces that I'm calling conservative. What I'm saying is, by definition, that means they do 0 work around a closed path. In a softer, more English, more intuitive way, just notice that any of the forces I just mentioned as conservative, particularly the gravitational force and the elastic force, the two that with which you are familiar, not only do they have like a position dependency to them, like there's like r squared in the denominator of both those forces, but more to the point, they are associated in our minds with some kind of equilibrium orientation. Like gravity always wants to bring you to the ground, to the lowest possible point. And springs always want to bring you to the center, to the least stretched possible point, right? There's like a place that there's a preferred orientation or configuration that seems to be associated with these forces that I'm calling conservative. That is generally a giveaway that we're talking about a conservative force. But why? How does this address? And there is no such thing as equilibrium associated with friction or tension or normal. But how does any of that address Olsmail's question, which, again, I'm just going to keep talking about until someone else asks a different question. But it's a great question. So here's how. Let's take friction as an example first, as an example of something that does not make the integral work out the way I would like, or it does not make it work out to 0. No problem. No problem. Totally. Oh. Did I tell the wrong class? Oh my God, no, this is my fault. Yes, it's the other class that doesn't. One class does not have class today. Oh God, did I tell you? But you're right. I told you guys. That's totally my bad. No, we have this class today. I thought you guys were in the. Oh yeah. I understand what you're saying. I totally told you that. It's totally my fault. I'm glad you're here now. For anybody this class is happening right now and will be taped and shown to the other group. It's the other group that I can't meet today because today's on a Monday schedule. But I told you guys that because I got confused. Okay, I apologize. Anyway, I'm glad anybody's here. That's great. And any of your peers who are not here because of something I said, It is my fault. You could tell them, and I understand that, but please tell them to watch this tape. I mean, this video later. All right. If I do anything besides just talk about how we're having class. Okay. So, friction. Look at friction as an example. Let us say, let me get an object. Let's say, I mean, I don't really have a tabletop. Okay. Say this thing is on a tabletop, right? So I pull it to the north for a while. I displace it to the north by pull. This is so ghostly. You understand what I'm saying? Say I take an object and I pull it across the floor toward the north for a certain number, for 5 meters and with 100 newtons of force. You don't have to get bogged down in the number, but just to make it concrete. So it's for 5 meters and 100 newtons of force, and I'm pulling it to the north. Let's talk about what friction from the floor is doing during that time. During that time, as I'm pulling the object to the north, friction, of course, is opposing the motion and pulling to the south, right? I mean, friction from the floor. So if I pull this thing with a force of 100 newtons, and I pull it for 5 meters to the north, friction is pushing or whatever back with 100 newtons of force to the south, while the thing is displacing to the north, right? The force of friction is opposed to the motion. The force of friction, let's say, has a negative sign. The motion, the displacement, let's say, has a positive sign, right? So it would be like, so stay with me. You don't have to stress about the numbers, but just if something is going to the north on a rough floor, then friction is pushing it to the south while that's happening. Friction opposes the motion. So friction would do negative work on the object while the object travels 5 meters, right? Friction would do negative 500 joules of work, and it would thereby take away 500 joules of kinetic energy from the object. It would slow down the object. That's what friction does. I don't think that's a surprise to anybody. I don't mean that as some deep new point. I think everybody is probably clear on that, right? That while you move this way on a frictional floor, friction is doing negative work on you, lowering your kinetic energy, slowing you down, or at least trying to slow you down if nothing else is going on. So in this example, friction would do negative 500 work. Negative 500 joules of work. The integral on the way out would be the dot product of a negative times a positive. Technically, it would be a vector times another vector magnitude times the cosine of 180 degrees, right? And the cosine of 180 degrees is -1, right? So technically. So now I'm following Osmail's question, because it's like, so right. If you did the integral out, you would do the dot product, which means the magnitude times the cosine of the angle between them. The two vectors are opposed to each other, so the angle between them would be 180. So the cosine would be -1. So you have a negative times a positive, use negative. You'd have negative 500 joules of work on the way out. Now watch this. Maybe Osmail already sees where this is going. But now, as I bring the object back to the south, now its displacement is to the south, but friction always opposes motion, always opposes displacement. Friction would now flip, right? The force function of friction actually depends on the direction you're going. So now on the way back, your displacement flips, but vector flips, but so does your force vector. So on the way back, the magnitude of one is 100, the magnitude of the other is 5, but the angle between them is still 180 degrees. It's still 5 times 100 times -1. On the way back, right, because the force function of friction technically is dependent on, like the direction of friction is technically dependent on the direction of velocity, right? It's not dependent on position, but it is dependent on motion, on velocity, friction is. Right? So on the way out, friction does negative 500 joules of work. And then on the way back in, according to the math of negative times a positive is still a negative. And according to the English intuition, on the way back, friction's still slowing us down, still robbing us of energy. It's still doing negative work. So the total amount of work that would be done by friction around a round trip would be negative 500 plus another negative 500, i.e. negative 1,000 joules. And again, I don't care about the number so much as I care about you're just compounding negatives when you do a round trip with friction. You have this huge net out of the whole thing. You have a net loss of energy. And another intuitive way to put it is if you rub against the floor on the way out and then you rub against, okay, cool. Phew. Thank you, Ultimate. Nice. And she can like triple dip that sucker, right? She could do it into the question portal and the closing the loop portal. But no, I'm glad. And it's a great question. Okay. And honestly, to everybody, it's not just about Ultimate. Like, I'm glad someone's actually thinking. I'm sure many of you were thinking of that. But I promise you, what I just said to her is like what I wanted to say anyway. It's like super important. And that's all in contrast. That is all in contrast to, say, gravity. Which with gravity, and I won't drag it all out. I mean, I think many of you could see where this is going, but look, it's so simple, but it's so different. Gravity, if I throw something up a height h, if I throw it up a height h and call up positive, let's say, so on the way up, its displacement is positive h, and its force, the force on it, is down mg, right? So it's negative on the way up. Gravity's pulling down, it's going up. So on the way up, gravity is doing negative work, negative mgh. Where did I get mgh? The force is mg, the displacement is h. So on the way up, the work is negative mgh. But then we get, and so of course the thing is slowing down. Like if I just threw it up on the way up, it's slowing down. Then it gets to the top. Now it's falling back down to where it came from. And so now its displacement flips. Now its displacement is negative. But the whole distinction, and again, I'm just spelling this out because it's like really fundamental. It's really big. I know Al Smile gets it now. I know she doesn't need to hear this part, and maybe some of you don't, but it's just weird that on the, as simple and similar as it is on the way back down with gravity, gravity's still pulling us down. So gravity's still negative mgh. It doesn't flip. It doesn't care what we're doing. It only cares where we are. Gravity is always pulling us toward this equilibrium thing called ground. So on the way up, the work is negative mgh. On the way back down, technically it's a negative times a negative. It's a positive, right? They're both aligned. On the way back down, it's positive mgh is the whole dot product. And therefore, on the way back down, we're gaining energy. We're picking up speed. Now, all right, okay. So again, great question. I'll stop saying great question now. And great point by Abdel that I totally messed up the entire announcement of this whole class. I'm so glad he actually is here and everybody else. Okay, so from now on, any force that will do net work zero around a closed path, we call conservative force. We designate it F sub C. Okay, and any other force we don't. Now, this gives us a big luxury, knowing that some forces are conservative, knowing that some forces around a whole round trip will not alter the energy of a system. Now, they will in progress, but they won't net at the end of the whole day. So if I throw something up and it comes back down, what I know is by the end of that whole closed trip, round trip, at the end, the total amount of kinetic energy that the thing started with will be exactly what it has at the end. So what that means is it gives us a shortcut ability. And this is all that I'm about to show you, but it's a major. It gives us a major predictive power and ability to shortcut. Oh, sorry. I really do think, oh, someone's in the chat, or that was, okay, cool. Okay. And I still want to say again, another shout out to William, to all the Williams. If your name is William anywhere, I shout out to you, but particularly William C, who I think you notice the more I do write on the board, the less it does disappear. I think he's totally right about that. Okay. So here's what we do from now on. Like really the whole world could be understood in terms of work and the transfer of kinetic energy. Work is transfer of energy. Energy is the ability to do work. Work is getting something to move. Energy is the ability to get something to move because you yourself are moving. Like really, that's like the whole package. And hopefully it makes some sense. But because some forces are conservative, it gives us this luxury where we can say from here on in, if a system is subjected to only to conservative forces, such as our mass on our spring here, the only force doing work is the spring force. Like in homework 1, the whole thing that we've been talking about for a million years, that mass only has one force doing work on it. It is the spring force. The spring force is conservative. It always wants to bring, for the exact in the same way that gravity is. It always wants, when the mass is traveling that way, the spring is pulling that way. When the mass is traveling that way, the spring is always pulling it toward equilibrium. So when we pull the mass away from equilibrium, that is just like pulling something up from the ground. As we pull something up from the ground, it's losing kinetic energy, it's losing kinetic energy, it's losing kinetic energy, and then we hold it right here above the ground, and it has no kinetic energy, something above the ground. Just like when we're holding the mass away from the equilibrium position, it has no kinetic energy. And we can end our discussion and say, so it has no energy. But the thing is, someone's here, but the thing is, we did all this work to get it there. We had to do, it's not just there by accident. If it's away from equilibrium, someone had to do work against a conservative force to get it other than at equilibrium, right? So we did all this work to get there, and we know how much work we did. In the case of gravity, it would be mgh. In the case of spring, it would be 1/2 kx squared, no problem. Thank you, no problem. In the case of the spring, it would be 1/2 kx squared. We did all this work. We gave it all this. We're doing all this. We're giving it all this energy, presumably. But then we stopped. It stopped. So it seems to have no energy. But now we also know. We know that if we let it go and we let it return to the equilibrium position from which we brought it, we know exactly how much work will be done on it on the way back to equilibrium, because necessarily it will be the same amount as all the work that we just did to bring it out there. We can easily, perfectly predict how much energy it's going to gain on the way back. So we can predict how much kinetic energy it will have by the time it arrives. It'll have whatever it had at the beginning when it started, because we know that around an entire round trip, the net change should be 0. So instead of redoing the calculation or redoing the experiment for the back journey, like anytime we bring something somewhere under the presence of a conservative force, anytime we bring something away from equilibrium, instead of having to do the experiment and the prediction and the calculation twice, we just say, oh, we know what's going to happen on the way back. It's going to be the mirror image of whatever happened on the way out. Because we're talking about conservative force. I mean, if and only if we're talking about conservative force. So, I just totally lost my train of thought. So we say that all the work done and all the energy that we seemingly were giving this thing as we brought it away from equilibrium, we say the object is storing that energy in the form of potential. We say that the object, we say that any one-way trip that is made under the presence of only conservative forces, any one-way path, we treat as the outward bound leg of what will ultimately be a round trip journey. And we say that even though the thing is sitting there right here with no kinetic energy, even though it seems like all the work we put to get it there just disappeared, since we know that someday it's all going to come back with the exact same amount as what left, we say all the energy here is being stored in the form of potential. Potential energy then, potential energy is the work that we have to do against a conservative force to bring a system away from equilibrium, or conversely, in my head, more easily stated, potential energy is a prediction of, but a fully accurate prediction, like a fully confident prediction. Potential energy is the amount of work that will be done by the conservative force to restore an object to equilibrium. That's what potential energy is. We say it's a prediction of how much energy will be done, how much work will be done by a conservative force to restore something to equilibrium. It's a prediction that we can confidently make only in the case of conservative forces, because we know what conservative forces by definition will do a round-around trip. So it's a way of treating any one-way trip as just the first half of some possible round trip. So, and I'm going to write this down mathematically now, and then we're going to move on. First of all, no, so potential energy is not a memorizer. You can't say potential energy of a system is always mgh, or potential energy is always 1 fkx squared, or something like that. Potential energy, first of all, is a function that is associated only with conservative forces. There's a different one for every there's a different potential energy function for every different conservative force. Potential energy associated with that conservative force is the amount of work that that conservative force would do to restore a system to equilibrium. So potential energy is an integral. It's the path integral of what a conservative force will do from there to here. If there is some initial spot and here is the equilibrium spot. There's no such thing as potential energy associated with friction. There's no such thing as There's no such thing as tension potential energy. There is spring potential energy. There is gravitational potential energy. There is electrostatic potential energy. In each case, it is the work done by that conservative force to restore an object to equilibrium. Thus, I'm saying the potential energy. So I'm just writing now the equation that you saw at the bottom of the first page when we started today. So the potential energy, well, here, let me write it first this way. That's Yiddish for I can't speak Yiddish anymore. Okay, this is a bit of a mouthful. Wait, something in the chat. I think it was just a thingy thing. Oh, yeah, no problem. Okay. Okay. In a way, it's so if you're following what I'm saying, first of all, remember, that integral, you're hopefully starting to recognize that path integral every time just means work, right? That path integral means work. But now I'm specifically putting a C after every F that I write in it to highlight that we're now talking about the work done by a conservative force, either gravity or a spring force at this stage of the game. And so now I'm saying that, so I'm saying we're still saying work is the transfer of energy. When I push you positively from here to there, I give you kinetic energy. Now we're just elaborating further and saying, okay, yeah, but if the thing pushing from here to there is a conservative force, then if you're going in a certain direction, we'll say that you're gaining potential energy. But notice, if you're really carefully tracking, like the way I'm putting my subscripts, and I'm trying to be careful about that, the way I'm putting my subscripts and the way I'm putting the limits of integration, if you look back on the first page, you'll notice that the two equations on the first page are like almost look like the same equation, and they're like kind of easy to conflate. But the difference between the two equations on the first page is one of them only deals specifically with conservative forces and potential energy, and two, its limits of integration are in a different order from the other one. That is not a typo. And if they aren't in a different order, then there is a typo. What I'm saying here is potential energy goes in the opposite direction from kinetic energy. When I'm pulling something away from equilibrium, I'm giving it kinetic energy, but it's losing potential energy. Potential energy is what the thing will gain when it starts coming back, right? So in the simplest case, if you look at the top equation here with the red, if you look at the simplest case, if I let the spring go, if I let the mass go from some arbitrary spot, call it x naught, right? Which I could have called x1 or I could have called x2. Like this can be a little confusing, but if I just pick any arbitrary initial spot, call it x naught, and I let the mass go from there, the work that the spring is doing on the mass as it brings it in from x naught to 0, like if I'm integrating from that place to the equilibrium, then the work that the spring would do to bring it in from x naught to equilibrium, that amount of work that the spring would do is what we're calling the potential energy that the thing has over here. In other words, the farther away it is, the more energy it's going to gain on the way back, the more we say it has potential energy. Even as I'm saying this, I haven't made a mistake, but I'm even hearing what I'm saying. It sounds confusing. I am saying that potential energy is a prediction of what will happen on the way back. So we integrate on the way back. The more work is going to be done on the way back to equilibrium, right? The more kinetic energy that we will gain on the way back is the more potential energy that we have before that happens, right? Some textbooks, if you're ever trying to get more help with this, like online or Khan Academy or the textbook, a lot of textbooks will flip the limits of integration and put a negative sign there. That's another way to think about it. I find that slightly more confusing because there's like a more negatives, but it might make more sense in English. What they're saying is potential energy is a measurement of the work you have to do against the conservative force to get something away from equilibrium. That is true. I'm saying the work that you have to do to bring something away from equilibrium is exactly the same as our prediction of what the conservative force will do to bring you back to equilibrium. They amount to the same thing. That's the whole point. Whichever way is easier for you to think about it, think about it. But at the end of the day, we're saying that that as you gain potential energy, you lose potential. And sorry, at the end of the day, we're saying every bit of potential energy that something gains by being away from equilibrium under the influence of a conservative force, every bit of kinetic energy it loses as it gets, I don't even want to say that. We're saying potential energy is the storage of the kinetic energy that we give something to bring it away. Potential energy will return. See, I'm saying it wrong again. I'm confusing myself. Potential energy is stored energy. When you're doing work against a conservative force, any amount of kinetic energy that seems to be lost, we know will eventually come back if we ever turn around and come back to where we started. So we say that potential energy is the amount of energy that seems to be lost temporarily, but is in fact being stored for later. Where is it being stored, you might ask? You might ask, wait, is it really being stored? Like, is it being stored in the mass? Is it being stored in the spring? Or is it being stored in what some textbooks will say in the spring mass system? It's up to interpretation. You could say whatever makes you comfortable. I'll tell you what I say. Potential energy is being stored here in our minds. It is a construct. We could do physics without it if we wanted to, but it just makes physics a lot easier if we use it. It's really what we're saying is potential energy is what we're storing in our memory as what was happening when we were coming out, and what we're predicting in our mind as what will come back when the object gets restored to equilibrium. It only works or is applicable to forces that we know in advance will produce zero net work around a closed path. So at the end of the day, the potential energy integral is necessary. Go all the way back to Olsmail's question now, and all the way back to the first page. Well, I'll try. Will I? If you go all the way back to the first page now for a minute, you notice, look what I was saying before. We're saying work is a transfer of energy. Kinetic energy is the ability, and you might want to write this down in English. Maybe I will in a minute, but if kinetic energy is the ability to do work by virtue of motion, right? Like the more motion you have and the bigger you are, the more you can get something else in motion. Then potential energy is the ability to do work by virtue of configuration or orientation. Oftentimes that means position, where you are. If you're in an unstable place, we know that ultimately when you fall back to or are released back to the stable place, the more stable place, the ground, the equilibrium, you will have a lot of speed by the time you get there and be able to do a lot of work on something. So potential energy is the ability to ultimately have kinetic energy due to the work done by a conservative force. So the work can equal change in potential energy in exactly the same way that it can equal change in kinetic energy, but the integral is in the opposite direction. It's what happens on the way back, or it's a prediction of what happens on the way back. Right? You notice the limits are flipped. It's not a typo. So what do we do with all this? sorry, and one for all my, I'm getting tongue-tied over the direction and everything. I don't want to make it any harder than it is. I think for some of you, and I'm betting, for example, Osmail, maybe it might have been totally intuitive and she might have been totally clear on it like 12 minutes ago. And then I talked so much that it might have gotten to the point where she was like, wait, is there something going on here that I'm not seeing? Like, why is he making this so complicated? I don't know if she was thinking it, but you might be, whoever you are might be thinking that. What I'm really just trying to alert you to is, in order to get the negative signs do matter. If you see the example of friction versus gravity, it's like all about the power of the negative signs. So it really is important to keep the negative signs straight. They can make all the difference in the answer. What I'm really trying to say, and this becomes very important in the concept of electric potential energy. In fact, I'll just skip a beat and just say the concept of a volt, as in a circuit, as in a battery, which we have to care a lot about in a few weeks or something, or a volt is a unit of electric potential energy per charge. A volt is a joule per coulomb. So this becomes very, very important and subtle in electricity. That's why I'm making a big stink about it right now. It's one of the reasons. And it can become a very thorny issue about like which direction to integrate in. What I'm just trying to say, if you look, when I write X2 and X1, I guess I did say it, but always, if you want to minimize negative signs, and if you want to minimize negative sign confusion, whenever you're calculating potential energy, integrate from the place of higher potential to the place of lower potential. Okay, as you see in these two examples. And notice what that really means in English is, I'm always saying that the potential energy, the difference in potential energy between two, the change in potential energy of a system between two positions is really a measurement of the difference in stability between two positions. Potential energy is really a measurement of stability. The more potential energy you have, the less stable you are. Equilibrium is the ultimate place of stability, and you have zero potential energy there. Okay, do you follow? So if you want to calculate how much potential energy something has, calculate from the less stable place to the more stable place, for what that's worth. Okay, now what does this all do for us? Once you, so in the end, well, yeah, no, okay. So what does this all do for us? Okay, I mean, this almost like sounds obvious now and sounds like a circle, and it is, but it's a circle that only applies to certain contexts. We're saying now, if all the forces doing work on something are conservative, if the only kind of forces doing work are those that are always eventually going to give back whatever they took, or vice versa, such as a spring force doing work on a mass, then we could say whenever it seems, we know that ultimately you're going to get back anything you gain. You're going to ultimately get back anything you lose. At any given moment where it seems like you have less kinetic energy than you started with, what we're saying is, yeah, but you're just storing it right now. You're holding it on as potential energy. So the more you lose kinetic, the more we say you're gaining potential. And then when you gain back the kinetic, we say you're using up that potential. So we can say from that, this allows us to say that there's this total amount of energy that we have that's the same no matter where you are, even if you're way away from equilibrium or at equilibrium, anywhere you are, anywhere. as long as the only forces doing work on you are conservative, we can say you have this lump of energy that's never changing. That's actually really convenient because we're always looking for constants that underlie the surface of apparent variation, right? So we can define this thing called total mechanical energy. We can define it, your total mechanical energy from now on. And that will mean all of your kinetic, all of your 1/2 mv squared at any given moment. When I say you, I mean if you're a system, a mass, plus all of your potential, so your total mechanical energy at any one, oh, and I should really say, sorry, the total mechanical energy of a system at any one position in space, I should really say that, of a system at some, how can I make this? So you take a system at a given position, at a given point in space. Remember, all of this has to do with the consequences of forces acting through space from one position to another. This is all about force acting in space as opposed to time. Like there's a whole other construct that's parallel to this if we were navigating through time. And I'm not saying that you can navigate through one without navigating through the other, but we're looking right now, we're focusing on what's happening through space. So the total mechanical energy of a system at a position in space is all of its kinetic energy, which is always just 1/2 mv squared. That's what it's defined to be in classical mechanics because of the algebra we did last week. So all of your 1/2 mv squared plus all of your potential, which would mean all of the path integrals of all of the various conservative forces that might or might not be doing work on you. So there could be more than one. There most certainly could be more than one. All of those added together make your potential energy. And by the way, why could there be more than one? Example would be a spring that was vertical, as in fact you looked at in the first lab. At any given moment when you're going back and forth, I think you did, at any given moment when you're on that mass at the end of a vertical spring, at any given moment, you've got kinetic energy, some amount, plus gravitational potential energy, plus spring potential energy, totally conceivable. But that total, oh, sorry. And the whole point of that total mechanical energy is that whatever it is, if and only if all the forces doing work on a system are conservative, then at any given two position, energy is a constant, is conserved, right? And that's and I'm going to write one more thing. I do see the time. I'm going to write one more thing to bring this home to show you now finally why we got the equations we did for questions 4 and 5, and then we're finally done with all that. And tomorrow we do have class, thank goodness. So tomorrow we do question 9 and we finally move on with our lives, sort of. What I'm saying here is for a spring, the spring potential energy would equal the work that the spring would do to move us from some spot to equilibrium, right? And we figured that out already. That's 1/2 kx squared. The farther out you are, the more unstable place you are, the more potential energy you have, the more that whole integral is positive, right? So the amount of potential energy you have when you're far away from zero is the amount of work it took to get you to there and the amount of work that the spring will do to get you back from there, 1F kx squared. So for a spring is the last thing I'm writing, and then we're not, but you've seen this before. So I'm saying for a spring, so I won't go to the next page. So I'm saying for a spring, for a mass on a spring, compare any one spot, its total energy, it will equal the total energy at any other spot. That's the truism, the GDP, for masses on springs. That's where that came from. Now, this was many days building up integral path, closed path integral, kinetic potential. But now you see energy conservation at the end of the day to us as physicists means that one path integral is going up while another path integral is going down. Okay, so we're done. So thank you for being so patient. Sorry about the confusion in my class. I totally get why you were confused. I apologize. And if you missed any, this is all being taped, but it's not on you and you don't have to explain it. And I owe you an apology, and please tell your friends. And I'm here for any questions. Actually, I'm here in my office for any questions for a couple of minutes, but you can go. Thank you so much. Okay. Have a good day. Oh, I realize, it's a little earlier than I thought. Oh, I was looking at the wrong clock. Okay, but yes, I'm totally here. If you have a good day. Sorry, I actually ended early. It never happened before. Have a good day. Have a good day. Thank you. Stop the recording. Have a good day. Have a good day. Have a good day. Yes. Thank you. Have a good day. Thank you. Go ahead and stop the recording. Or I'm stopping the